Full screen. All right. All right. They have a video made a while back on inequalities, but a lot of those videos were made at the end of the day after, 3 classes in the spring during the early days of the pandemic, and we were all scrambling to get things done. So I thought I'd make another one and hopefully explain things a little more clearly. Repetition is my friend, I like to say on every test, and more times you explain something, hopefully you finally get it right and understand it at a deeper level. So we're going to start from the real basic consideration, and then we're going to build off it into the types of problems that we're going to work with the rest of the term. So solving inequalities. So we got a function y equals x minus 5. We want to know when x minus 5 is greater than or equal to 0. Not the most challenging question, but it's a starting point. So we can look at x minus 5. We know it's a linear function. And what we want to glean from this is that the inputs bigger than 5 get me positive answers. The inputs smaller than 5 get me negative. And what we call happening at x equals 5 is a sign change. We go from a negative to a positive in this instance. Doesn't matter what number we pick. We could pick 4, which is less than 5. We can see that 4 minus 5 is negative 1. Is negative 1 greater than 0? False. So this is called a sign chart. We put the number 5 in. Is 0 greater than or equal to 0? Well, that's true. So I guess I should put a little t here. That works. And then a random number, 6 minus 5, 1 greater than 0. That's true. Okay? You could see it from the graphical standpoint. Eventually, we want to see things hopefully from the graphical standpoint. We're going to be doing some more complicated graphs here in a moment. About 10 minutes probably. Because graphs at the calculus level give you a little more information about something that you might be studying. A position function, for instance, how many points of inflection it has. Sign chart doesn't give you the same accurate information. Well, I suppose it does, but you look at it slightly differently, I think. So in this case, our solution is 5. X is greater than or equal to 5, and we're going to introduce interval notation. Hopefully you had it in your last class. I use a bracket to indicate that 5 works. If I used a parentheses, you could see the diagram here that I'm sure you worked with in Algebra 1 or pre-algebra. So 5 doesn't work in this instance. If I was erasing the equal sign, then that would be the solution, and a parentheses in front of the number indicates that doesn't work. Equals, bracket, 5 does work. Okay, so we'll use interval notation as we go forward here. All right, so let's continue moving around the room. I'm going to have to move the desk from time to time. All right. So here we have same statement, y equals x minus 5, which we know is this graph with a sign change at 5. So we refer to 5 as a critical number. It is critical. And if you're running a business, probably important to know whether you're making money or losing money. And some of those numbers pop off the page at you, I'm sure. Now the question is, what happens if I hit that with an absolute value? Well, I hope you say these negative values here now become what? They become positive. And so when is x minus 5 greater than or equal to 0? Well, you can look at the graph and say always. Or you could still do a sign chart, plug a number in, put a million in, it doesn't matter, any number bigger than 5 gets us true, put a 5 in, gets us true, put a 0 in, 0 minus 5, absolute value of minus 5 is 5 greater than or equal to 0? So you can do a sign chart. I think looking at the graph was quicker than doing the sign chart. Just graph it, look, always positive or 0. Okay. Another operation basically does the same thing. There's another operation in math that takes this linear function, we turn it into a quadratic, so we don't have constant rate of change anymore. It's not constant anymore. We bring in a little acceleration into the picture. All right, we get a graph that looks like that. 5 is still critical. And it doesn't matter whether I put a 4 in or a -4, doesn't matter. Squaring a negative gets us a positive. Putting in a 5 gets us a 0. Putting in any number bigger than 5, I could do 5.5, doesn't matter. A half squared is a fourth, still positive. So that exponent yielded a positive response, except at 5, the critical number, which gave us a 0. Okay. So let's continue on with this conversation. X minus 5 again. This time, let's cube it. Throw some numbers in, like 4. User-friendly numbers, or 0. 0 minus 5 is fine. 0 minus 5, -5 in parentheses cubed. Minus 125. Is it greater than or equal to 0? False. Right? 5 still works, that's true. And putting a number bigger than 5, 6 or 1,000,000, doesn't matter. Cube it, it's true. All right. So let's look at it graphically. You would get something that looks like that. You would get a cubic graph. 5 gets me 0. Prior to 5, negative numbers. Negative numbers are not greater than or equal to 0, so that would be false. This number here would be true, and this would be true because these are positive and these are negatives. So did we have a sign change? Over here in the quadratic, yeah, you can still see it. We went from positive to positive. No sign change. In the linear, x minus 5 to the 1. Sign change. When we did it to the 2, no sign change. When we did it to the 3, sign change. Yes, sign change. The outcomes of the cubing process went from negative to positive when we did cubing. It didn't when we did squaring. It did when we did it to the first power. I wonder what it's going to be when we do it to the fourth. What's it going to be when we do it to the fourth? Well, that's still 0. So we put 0 in here. Minus 5 to the fourth. Minus 5 times minus 5 times minus 5 times minus 5. A negative 1 time is a negative. 2 times the product is positive. 3 times it's negative. 4 times it's positive. I get a positive answer. Put a 10 in. 10 minus 5 to the fourth. That's obviously positive. So what would that graph have looked like? Very similar to the quadratic. It's just, when you take a number like a half and square it, you get a fourth. When you do a half to the fourth, you actually get a 16th. So this is smaller until I get past the number 1. When I get past the number 1, 2 to the fourth, right? So it's going up quicker after we get past, in this case, 6, 1, just to give you a feel for what the graph looks like. But the discussion we're really having is about sign changes. So we know a 5 still gets us 0. What do we get when we use numbers less than 5? Positives. What do we get when we use them bigger? Positive. Okay. So now let's have you try your first problem that's a little more complicated. And we'll do it together in a moment, and then we'll start practicing them in class. So here's one that I haven't seen in the textbook, but I made it up. And the reason I used it is I want you to think about the fact that the exponents, in this case, I'll write the 1. Right? I'm going to add another I'm going to add another one in here. I'm just going to put x there as well. Okay? Because when does something equal 0? Well, if I put an 8 in here, 8 minus 8 is 0. 0 times anything is 0. When I put a -3 into this parentheses, if I make all the x's -3, I highlight this one because this one becomes 0. It doesn't matter what the others are. 0 times anything is 0. If I make all the x's the number 2, doesn't matter. That one doesn't matter. 2 minus 2 is 0. 0 times anything is 0. And when I let x equal 0, doesn't matter if I 0 minus 2, 0 plus 3 cubed, 0 minus 8. If I make that 0, 0 times anything is 0. So I have a bunch of critical numbers. So we're going to put them on a sign chart first, right? Or you can think of it as a sing chart. I want those critical numbers singing to you. I want the number 8 singing to you. I'm going to put a dot there. I want the number -3 singing to you. I'm going to put a dash there. I want the number +3 to sing to you. I'm going to put a dash there. And I want the number, let's make this x squared. Let's make it x squared, right? If you put a 0 and 0 squared, 0. I'm going to put a dot there. Now the question is, why am I doing that? Why do I think that that might be helpful? Well, it's all about sign changes. Do I get a sign change here? In other words, if I put a 6 or a 7 here, 6 or a 9, sorry, right? Something like that. 6 minus 8, -2, but what's the absolute value of -2? A positive. 9 minus 8, 1, absolute value 1, a positive. I didn't get a sign change. And this is a product, right? So if I told you you have a positive times a positive, what's your outcome? It's bigger than 0. But if something changes signs, well, it's not bigger than 0 anymore. So this is all about, does something change signs at these critical numbers or not? So let's put the number 6 in here. 6 plus 3 cubed, positive. Put the number 9 in here. 9 plus 3 cubed, still positive. 6 minus 2, positive 4. 9 minus 2, positive 7. It's not going to change. What I'm doing isn't going to change that, right? So, it's not going to affect the product. When I put a 6 or a 9 in here and square it, positive. Okay? But what happens when I put a 6 or a 9 in here? Stayed positive. Maybe that wasn't the best one to show. Maybe I should have shown -2 and positive -4. Okay? So if I put -2 or -4 in here and square it, positive. -2 or -4 in this parentheses, doesn't matter, negative. -2 plus 3 cubed, well, that's a positive number. -4 plus 3 cubed, that's a negative. Makes a difference here. -4, -2 minus 8, it's going to be positive. Doesn't matter here. Makes a difference here, so we get a sign change here at -3. That's why I'm putting a dash. Okay. Again, this is the first time that we've talked about this, just like everything else we do. Day 4, the 4th day that you do these problems and you get a chance to work through them, hoping it makes a difference. And I'm hoping the fact that you do it 4 days in a row and then every test the rest of the semester makes a significant difference in your understanding. All right, so now all I'm going to do is try some things. Okay, I'm just going to plug some numbers in. I'm not going to graph this one because honestly, I'm not sure how this is going to affect the graph. Pretty sure. I don't think it's really going to do anything different than what it will as we look at some in the future. But we're just going to do a sign chart or a sing chart. So I'm going to pick a number bigger than 8, a million. I'm going to put a million in here. Pretty sure that's a positive. A million plus 3 cubed. Pretty sure that's positive. A million minus 2 seems to be positive. And a million squared seems to be positive. I think this is true. And because it's equal to 0, I know all of these numbers are true in this context as well. So I'm just not going to put a t here, t here. Okay, we just know that that's also true. I think this is going to be true without even looking at it, because I know that I don't get a sign change here. We looked at that at the beginning of the video. So I'm going to pick a number, though, to do it, to prove it. I'm going to pick a 5. A 5 minus 8 absolute value, still positive. Yeah. 5 plus 3 cubed, positive. 5 minus 2, positive. 5 squared, positive. Nothing changed. It's still true. But I got a feeling that this is going to be false, because I think I get a sign change. What the heck did I put that there for? This should be 2. Okay, I'm not going to go back and do this video again, so excuse me. I caught the error. That's one of the most important things in mathematics, is to find out when you're wrong. I just did, and I corrected it. So you feel free to do that the rest of the semester too. Okay, so that's the critical number here. I don't know why I wrote positive 3, but I'm sure you saw it. Let's see now, where am I? I forgot where oh yes. I don't think I'm going to get a sign change here. Did I already do that one? I'm going to get a sign change. I don't think I did that yet. So let's try the number 1. Should be false. So 1 squared is positive. Oh, 1 minus 2. Oh yeah, we did get a sign change here. 1 plus 3 cubed, no sign change. Never going to get a sign change here. We're going to stop looking at that. Okay. Yeah, so we got a sign change. And if we get a sign change, a positive times a negative is a negative, times a positive is still negative, times a positive is still negative. Is a negative number greater than or equal to 0? False. It is not greater than or equal to 0. I'm pretty sure the next number I plug in is also going to get false. Let's see if I can show that a little more clearly. I think that's going to be false too. Let's try -1. I think it's going to be the same situation here. Oh, I'm on this side of 0 now. Okay, so -1 squared is positive. -1 minus 2, that's still negative. -1 plus 3 cubed, that's still positive. That's always positive. Same situation, so it's still false. I'll leave that one to you if you want to do it. It's going to be true. Okay, so how would I have done this? Once I identified the critical numbers and whether there were sign changes there or not, go through that again. At 0, it's even, no sign change. I use a dot. At 2, it's to the first power. That means there's a sign change in the product. And therefore, I'm going to put a dash at 2. At -3, it's odd exponent. There's going to be a sign change, and there's not going to be a sign change here. So once you pick a number like 1,000,000, positive, 1,000,000, positive, 1,000,000, positive, always positive. This is positive. So therefore, if it's positive, it's greater than or equal to 0. It's true. No sign change, it's true. Sign change, it's false. So I guess I want to write false. No sign change, it stays false. Sign change here because we put a dash, that makes that true. So the answer was -infinity to -3. -3 works because when I put a -3 in, it equals 0. Union means also 0 works, so I got to put it in there. Union 2 to 8 to infinity, so I can show that as 2 works to infinity. And that's how we're going to answer our calculations with interval notation. All right, continuing on. It's going to be a long video, but it incorporates a lot of problems that we can do the same way. We can answer these all the same way. So division is a form of multiplication, right? I mean, I could do 4 divided by 2, or I could express it as 1/2 times 4. So the same process we can study with sign charts. I won't graph. These are rational functions. They get tricky to graph, take a long time. So we will just do sign chart here. Can you identify the critical numbers? And can you write the dashes or the dots? Pause the video and try. You can try this problem on your own now. You actually have enough information to give it a go. With practice, you'll get faster and better, hopefully. I'm going to look at it and say, oh, odd exponent, 4 is critical, odd exponent, sign change. Dash. -5, even exponent, no sign change. Now, I am just going to pick a number bigger than 4, any number bigger than 4, 4.1, 4 million, anything bigger than 4. 10. 10 minus 4 cubed is a positive. 10 plus 5 squared, that's always positive except at the number 5, right? So there's not going to be a sign change here. A positive divided by a positive, is that greater than or equal to 0? True. Then that's false. -5 is false, actually, because you can't divide by 0. That's why I put it there. So -5 does not work because you're not allowed to divide by 0. I mean, you know, if you could divide by 0, we know that 6 divided by 2 is 3. It's got an inverse because 6 is equal to 3 times 2. If you thought 6 divided by 0 was 0, then 6 would have to equal 0 times 0. That makes no sense. I don't know what it means to divide nothing into 6. I know 6 doesn't go into anything. I know 6 goes into that 0 because the inverse, 6 times 0 is 0. That works. Can't divide by 0. Try to remember that. Okay, so that doesn't work. And there's no sign change. That doesn't work either. So pick any number less than 4. Let's pick 0. 0 is less than 4. 0 minus 4 cubed. 0 minus 4 cubed over 0 plus 5 squared. That's a -64. That's positive 25. That's a negative number. Is it greater than or equal to 0? No. We knew it anyway. If that's true and there's a sign change, then it's false there. Okay, you can try a number less than -5, it's going to be false. That's the purpose of the videos, to learn how to do these quickly. All right, but let's go back to products. Your chance to do one now. All right, so pause the video and you try that problem. X minus 2 squared, x plus 4 to the 5th. I'm going to do a sign chart and I'm going to do it graphically. I want us to learn how to do it graphically. All right, and I don't think I've talked about that yet, so really pay attention to this one. Sign chart, +2, even exponent, no sign change. -4, 5th power, odd, sign change. Pick a number bigger than 2. 1,000,000 squared. 1,000,000 plus 4 to the 5th. Less than 0, false. False. True. That's what you should get. Okay. You can put -1,000,000 in here. -1,000,000 minus 2 squared. Well, it's going to always be positive. -1,000,000 plus 4 to the 5th. Well, -1,000,000 plus 4 is a negative number. And if I do that 5 times, you can do it. Negative times negative, positive, negative, positive, negative. I get a negative. What's a positive times a negative? A negative. Is a negative less than 0? True. Now, I want to do this from a graphical standpoint. Okay, so let's get this out of here. Polynomials. Y equals x. Up to infinity. X squared. Up to infinity. X cubed. Up to infinity. This one goes up faster than that one, and that one goes up faster than that one as numbers get past 1. Okay, so polynomials tend to have end behavior going to positive infinity or to negative infinity. Right? So the end graph is going to look one way or the other. So which one are we going to get? Well, all we got to do is pick a number bigger than 2 and find out if we get a positive or a negative, and then draw it backwards. And you can look at the graph and you can tell when you're positive and when you're negative. And we want to be negative. We want to be less than 0. So I'm going to pick 1,000,000. 1,000,000 minus 2 squared, 1,000,000 plus 4 to the 5th. That is definitely positive. That means I'm going up. So I'll draw it backwards. No sign change. Sign change. Now, this over here, if you put it in Desmos, would have a little different look to it. So I might as well talk about that a little bit. So it's going to actually, just like the cubic did, the rate of change at -4, pretty infinitesimally small, goes to 0. Why? Because if I pick the number like 2 1/10 minus 2, I would do, I picked the wrong number. If I picked the number, I should have thought positive over here. If I pick -3 9/10 plus 4 is actually 1/10. And 1/10 times 1/10 times 1/10 times 1/10 times 1/10. I don't know how many times I did it, but it would have 5 zeros in it. That would be 1 over 100,000. You would not be able to see the difference between a height of 0 and a height of 1 over 100,000. So rates of change at those critical numbers, something you study at the calculus level. All right, so that's what the graph would look like. So now I look at the graph and I go, when am I less than 0? Oh, negative infinity to -4. After that, it's always equal to 0 or above. So that's where the graphical gives you a quicker answer. Okay, so we'll be practicing these in class, and believe me, you don't have to learn it on the spot. Again, I tell you, if I hit a new math concept, I read about it, I know it doesn't make sense to me day 1, I shut the book, I come back to it the next day. I'm talking 3-4 minutes. That's all I spend, right? But if I do that 4 days in a row, something magic usually happens, as in, that's making a little sense right now. It takes the brain time to connect those synapses on any topic you look at. All right, so here's another one, division again. It's all about signs. What's a positive divided by a positive? That's greater than 0. What's a positive divided by a negative? That's less than 0. What's a positive divided by 0? That's undefined. So these are the things we're considering. But notice what I was always talking about, the number 0. And if you don't make this thing, you're positive, right? If you don't make this thing greater than or equal to 0, then we can't talk about products, right? We don't talk about when is a product bigger than 1. It's not that easy to contemplate. So first step is x minus 2 over x plus 4 minus 1. Then we can talk about it being bigger than 0. I didn't divide by a negative. I didn't add it. I didn't divide or multiply by a negative, which I hope you know, if we said 5 is less than 10, if I hit this with a negative, I multiply both sides by a negative, I guess what? Negative, just hit it with -1, right? Well, then that's actually bigger, right? But if I have 5 plus 1, which is less than 2, and I subtract 1, well, that stays the same, right? So addition and subtraction doesn't change the direction of the symbol. Division and multiplication by a negative does. Useful, hopefully, review from previous level. All right, so now the question is, are we getting better at working with fractions? And remember, this is 1 over 1. Right? We need what? We need it to be x plus 4. So what do I do to that number? I multiply it by x plus 4. So what do I do with -1? I multiply -1 times x plus 4. And you got to be careful with that. So that's minus x minus 4. Right? And I'm putting x minus 2 over x plus 4 with that. And so there's a common denominator here. So I really have this. And I want to know when it's greater than 0. This isn't going to be too bad, because what happens to x minus x? That cancels. And I get -2 minus 4 is -6 over x plus 4. There's only one critical number here. So I don't think I'd graph this. I'd simply put -4 there. We know that's not going to work. Can't divide by 0. So then the question is, we know there's a sign change because that's to the 1. So pick a number bigger than -4, a million. If you put a million in here, you get -6 over a negative. You get -6 over a negative number. When you divide a negative into -6, you get +6. Is that greater than 0? Yeah, so that's true, that's false. So interval notation, -4 to infinity is your answer. Okay, I know this is a long video. Okay, so hang in there. Last topic that's going to come out of this that we're going to practice on is, can you see it? Yes, absolute value functions. Okay, so let's look at the absolute value of x. All right, we started with y equals x. Oh, geez, sorry, I was thinking about the last problem. There's y equals x, right? That's this graph. What is happening when I do this? It is turning into this graph. The name of the graph on the left is -x. The name on the graph on the right is +x. Right? I mean, if I throw y equals absolute value of x and I use -5, the absolute value of -5 is 5. If I plug -5 into that function, I also get +5. We call that a piecewise function. So I could have defined this to be 2 pieces. 1, -x, provided you're picking x is less than 0. +x, providing you're picking x is greater than or equal to 0. That's written in pieces. That's written as a singleton. Okay, so let's examine this. I hope a critical number is jumping off the page at you. I hope it's 3. And I hope this looks something like what we've been practicing in class, right? That's got a vertex. So do absolute values, except the rate of change is linear on the left and right side. And we know how to write the equation of a line. So let's find out what the equation of the line is here. All right, so 3, 4. I hope we see that. 3, 4. And I always, same thing here. That's cup shape up. This is V shape up because it's positive. So we know we have a positive. And if you're going to cut through the y-axis, I'm just going to draw whatever the scale is because I'm running out of room here. But you should always do the vertex and the y-intercept of the graph. So we plug 0 in and we load it. Yeah, Alicia, right? I like the loading symbol. So 0 minus 3, -3, the absolute value of 3, 3 times 2, 6 plus 4. We know it's that now. Okay? Well, I got a linear equation here. Let's see what the equation is. That passes through 0, 10, from left to right I'm going now. and 3, 4, because that's kind of the what word do I want to use? The standardized method we've been using the smaller x first. So I just want to talk about this piece right there, that piece right there. And I know that piece is only defined when x is less than 3, right? This is where you get the sign change. So this piece is only defined for x less than 3. What did I do from 10 to 4? I went down 6. 0 to 3, I went up 3. And so what's minus 6 divided by 3? I'm not going up at 2 to 1. I'm going down at 2 to 1. Okay? This side here is going to be the same. Right? So the two pieces to this, and we'll look at it more in class. We'll look at it more in class. Two pieces are as follows. Boom, 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 boom. We want to look at when x is less than 3, and we want to look at when x is greater than or equal to 3. And it's real easy to do. All you have to do is change the absolute value sign to a parentheses and put a plus minus there. This is the minus 1. That's when it's less than. So minus 2, x minus 3 plus 4 gets the job done. I ran out of room. I'm sorry. I should write that more clearly. So we have minus 2, the downside, minus 2, parentheses instead of absolute value. And that occurs when x is less than 3, positive 2, x minus 3 plus 4, when x is greater than or equal to 3. Now, why does that help us? I'm going to do a problem for you. I know it's a long video, okay? Just following at this stage. So what if I had a problem like this? 3, absolute value, x minus 5 plus 7 is less than, let's make it some friendly numbers here. Let's say 10, 15, 22. Okay, now I could graph it. I'm probably faster graphing it, some shortcuts, but I just want to make sure that you've got something to get grounded with first. Well, the first thing I'm going to do is I'm going to identify 5 as the critical number. Okay, is that? I haven't done this in a year. All right, let's cut to the chase. I'm going to change this to plus or minus 3, x minus 5 plus 7, and I'm going to set it equal to 22. I just want to find, you got to forgive me here because I'm trying to remember what the shortest way to do this is. Oh, sign chart. I'm sorry. So it's actually easier than what I'm giving you right now. No, that's right. So plus or minus 3, x minus 5 plus 7. Yeah, I got you. I got you now. Sorry, it took me a while. So we're just going to solve that. Okay, and to solve that, we do it in the two parts. We do positive 3 and negative 3. I'll do the negative on this side. Takes a little while to write that. Now, positive on this side. Took me a moment to remember where I was in this whole scheme of things. All right, so subtract 7, divide by negative 3, add 5. That's a critical number. Over here, can we see this? Yes. Subtract 7, divide by 3. You'll notice we have a little sign change there. Add 5, 10. So what are my critical numbers? 0 and 10. And I know that these are to the first power. Or having done these forever, I know there's going to be a sign change. So all I have to do is pick a number bigger than 10 and find out if it's true or false. Let's put 100 in here. 100 minus 5, absolute pretty big positive number times 3, big positive number, plus 7, big positive number, less than 22, false. And I'm going to get sign changes, and I'll show you why in a second. So your only answer is x value is less than 10. Yeah, I don't have an equal sign. Greater than 0. That's what we're going to be practicing. Now, what we had here, you can replay any part of this video, right? Was an absolute value. 5, 7 was the vertex. Height of 22 is up here, and I want to be less than 22. There's 3 sections here. There's A, B, and C. What were A, B, and C in our? We had a 0, we had a 10. That's our A, B, and C intervals. And what interval gave us the negatives? The ones between 0 and 10, right there. Okay, running out of breath here. So I probably should have spent a little more time on that, but we're going to do it in class. This is just an introduction. Okay, and it's a lengthy one. Probably when I assign this money, I'll probably tell you to look at it in two parts. Go look at it for 20 minutes and then go do something else, come back and look at the second half. But just let it sink in a little bit. And we're going to start working with it. All right? All right. We'll see you I guess you're watching this on Monday, so I'll see you tomorrow, Tuesday.